This is on beginning transformations. Let's review a little bit of things about the coordinate plane. First off, we call the coordinate plane. Coordinate plane is flat plane with a grid on it. We frequently talk about it as the Cartesian plane. It's named such in honor of the French mathematician René Descartes. René Descartes was a well-known French mathematician who worked in these types of areas. You see that the name comes from his name, at least for part of it. Talk a little bit about some reminders about transformations in the coordinate plane. We can start with just what they are. Here's Froggy. There you go, Froggy. Hey. Okay, so Froggy is here. Froggy slides over to here. We call that one a translation. Here's Froggy. Froggy turns. Or Froggy turns around like this. That's a rotation. Either clockwise or counterclockwise. Then there's reflection. So here would be Froggy. Reflection across a line is one way to have a reflection. It would be the image on the other side of it. Reflection across a line. There's also reflection in a point, which we'll talk more about later. Some of the terminologies that we'll use with regard to transformations include some that to me are a little odd, but we need to know them anyway. The one I most commonly used is the original, and from the original is the copy. Now other folks, although doesn't make a whole lot of sense to me, they'll say if you have an image, that what comes before it is a pre-image. Doesn't make a lot of sense to me, but hey, we can learn the terminology so we can use it all. If a point in particular is named A, then we'll name its copy or its image A prime. That's a little apostrophe, and we call it prime. That's how we pronounce it. You might also, if you make a copy of a copy, or the second copy, it would be two little marks, two little apostrophes or a quote mark, and we would call that double prime. So upon looking at a figure and its copy, you can tell which one's the figure original and which one's the copy by which one has the prime or double prime or etc. We don't usually go through a whole lot of them. Sometimes you'll see triple prime, but at some point you just get tired of making marks, and that goes away. A definition for us. That would be an isometry. An isometry is a transformation that preserves the size and shape so that the original is congruent to the copy. It's also known as a congruence transformation. Let's look at one of those here. This would be an example of a congruence transformation. This is an isometry. This is a translation. We can tell that the blue is the original because it doesn't have a prime, and that the red is a copy because it has the prime by each of its vertices. One terminology that we'll need to know here is a mapping form of terminology. That would be mapping. We would say that XY maps to, well, let's see what happens. Say if I take any point on the blue one, I'll move it 3 points to the right and down 1 to get to the new one. That's true for the C, over 3 down 1, A over 3 down 1. If I choose any point along on it, then it still is the same. That It works the same for each one of them. Every point will do the same thing. What happens is the x value increases by 3 and the y value decreases by 1. So one way to describe this transformation is x plus 3, y minus 1. So this is in the original, and this is how we see the copy. So we can see an example of it here. What is that transformation? Be aware. Find the primes. That means it's the copy. This is the original. So B goes 1, 2, 3, 4, 5 to the left, which is minus 5 for the x, and up 2, which is plus 2 for the y. X minus 5, y plus 2. Now, a vector. What is a vector? A vector, the definition, is a quantity with both magnitude and direction. Let's look at how to deal with some vectors. I'll draw one. If I can find my ruler. Okay. So I'll start with a vector. I'll draw one out for you here. This is a representation of a vector. It starts at point F and ends at point G. Notice there's no coordinates on this plane. There's no axis, no x, no y, no reference like that. Everything is relative to where it has been and to where it's going. This is a vector. It's a vector beginning at F and going to G. We can write that as the vector FG, and the symbol is an arrow on top with half of an arrow. The bottom part isn't there. If it were there, it would be a ray. That's the symbol for vector. It's not just a cute ray. So the vector that begins at F and goes to G. Magnitude is shown by the length. Direction is shown by the arrow. It has both magnitude and direction. It's the vector FG. We call the beginning point the initial point, and we call the ending point the terminal point, where it ends. Except nobody uses those names. Everybody calls the initial point the tail, and the terminal point the head. So here's the head of the vector, that's where it's going. Here's the tail of the vector, that's where it's been. We can also name it usually with a lowercase letter. I'll name this one just M because it's easier to use one letter, which is fine. In that case, I can go ahead and also call this the vector M, again with half an arrow. Let's some of the characteristics of this vector. The magnitude has two components. The first one is the horizontal component. That's how much it moves horizontally. So this is the horizontal component of the magnitude. And this one is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9. How do I know? Because I counted it. That's the horizontal component of the magnitude. And probably pretty obviously, this is going to be the vertical component of the magnitude. And it's 1, 2, 3, 4, it's 5. Okay. Horizontal component, vertical component combine to make the vector with the magnitude and the direction. And Another way we can talk about this vector is with regard to its components. We'll write it kind of like an ordered pair, but we're going to put funny looking parentheses. The horizontal comes first, and then the vertical. Notice this is the same order if this were on the x-axis and then we're on the y-axis, but it's not because we don't have any axes. Everything's relative to each other. So the horizontal 9 is left to right, just like x is left to right and is in the x position. The vertical component up and down, like y is up and down, is in the y position. And I put the numbers there. So I can talk about this vector in any of these ways. Okay, here's an example of some of the ways that we can talk about a figure. This one is on the axes, so we can use the mapping terminology. We can look at mapping of x, y goes to, well, let's see, let's look at, choose the same corresponding point. So I'll choose B and B. See what the motion of B is. B goes 1, 2, 3, 4, 5 to the right and 1 down. Or x plus 5, y minus 1. If we want to talk about it in vector terminology, it would look like this. And you might say, well, I only chose one point. I don't know that all the rest of them do the same thing. How do I know that? Is it always the case? Is it always an isometry so that the end figure is the same shape, and do all the others move the same? I appear to assume that. Okay, let's go back to Froggy. Let's see what happens to Froggy here. Here's Froggy. Let's notice where Froggy's left toe is. All right, I'm going to move Froggy's left toe over to here. Okay, there's Froggy's left toe. Oh my, it sure looks like the rest of Froggy came with his toe, and he's still Froggy. Well, let's check that out. Looky there, there's Froggy and his left toe at the initial position. Well, let's look at Froggy's, well, that one's a toe, finger, and then the one on this, down here, this digit. We'll take that one. I wonder if it goes the same. Well, let's slide Froggy's left foretoe there to the same place. And now Froggy's left hind toe is right there. Oh, what happened with it? Well, it went over and down, if you want to look at the components of it, over and down. It moves the same. Froggy is one and undefiled. He's still Froggy. When part of him moves, all of him moves. It's an isometry. Here endeth this lesson.